Lorraine is from the Material Engineering and Electrical Engineering Department with Dr. Shadi Daye, and I'm with Dr. Devor. So why do we need chronic preparations? Because when you have chronic preparations, you can image the mice awake. So you don't have to deal with all this unwanted effects of anesthesia. And also you can take a subject and monitor it in a long period of time. And they can also act as a baseline for themselves. And they can be imaged with different modalities. When you do acute experimentations, usually you can only image with one modality because it's just prepared for that, and you have a limitation of time. And it just decreases the number of subjects, so less mice, that's good for us. But it has some challenges because since the mice that we are using are like 20 to 30 grams, they are very tiny, and we need to find tools to prepare this. And also, they can lift up to like 4 grams on their head, so we cannot really put everything there so they can walk around. And healing is sometimes you need to take care of them, and even though you need to be very particular about it so that you can get like good healing. And also in order to image them awake, you need to train them so that they can be imaged like this. This is under 2-photon microscopy. When we look at the recording and imaging, I just wanted to summarize that there are like different types of electrodes which can be used for measurements from the surface or depth. They can be multi-channel or single-channel electrodes. And today we are going to actually talk about this. Sorry, I cannot see my. Yeah, sorry, it doesn't work. So we're going to talk about the multi-channel surface devices, the P.PSS devices. And Lorraine is going to explain the technical aspects of it. And for the imaging, you can have naive fluorophores or genetically or virally transfected indicators like GCAM here, or intravascular probes, all kinds of colors, or intracerebral probes that you can inject directly into the tissue. And also, since these arrays are transparent on the background, these also allow you to image something with an optogenetic activation. So I would like to mention a couple of recent studies that are done to prepare chronic animals, and I would like to mention my concerns about them. So here's one of them, and this one is like a flexible window which is only covered with a PDMS. So this one actually, the problem with the advantage of this is like you can stick some glass electrodes for injection or either recording. The disadvantage is you can only do this so far because every time you're giving the tissue some sort of damage. And also it's reported that like there's some air exchange between the PDMS, so you can see like bubbles under the PDMS, so your imaging quality is getting worse at some point. Here is another one who would allow you to introduce either an injection pipette or an electrode through a port. But on this, since you can see through this preparation picture, there is only one glass that is sitting on the skull. So there is a gap between the brain and the glass. So this allows like immune cells to wander around in this space, and then in the end, if you look at the first week and the third week, you can see that there's a lot of growth on the dura. So this makes the imaging quality worse. And here's another preparation which they called cranula because of a craniotomy and a cannula together. So they have had multiple models of cannulas so that they can inject either intracerebrovascularly or basically inside the parenchyma of the brain. And they can image next to that. The problem is they're not on the same site, so you cannot really see what the injection site looks like. If it's an intracerebrovascular injection, of course it doesn't matter like where you can inject it, but if it's intraparenchymal injection, you do not see the injection site. So what we tried to do is we tried to optimize some of these models and came up with a model that would allow us to image for a longer time without the regrowth of the dura, and also for the injection of several substances so that we can use these in combination. So here's what we came up with. And this is like a glass plaque on the left upper side, and next to it there's a glass plaque with a silicone seal, which looks like this. And this FITSI picture is taken like several weeks after the implantation. It's still looking good. It doesn't have any regrowth because these plaques, since they're just like having a little bit of pressure on top of the dura, there is no gap, so the immune reaction is minimized. And here we injected OGB and made some measurements. You can see the cells that are filled with OGB. Also, with the chronic devices and electrophysiological recordings, there are several papers around. I just put this because in almost every one of them, my point will be the same. Even if it's a rat or a mouse, when people are fixing these things, they use screws and acrylic all over the place, which just blocks the ability to image through those things. You can record for chronic time, but this will not allow you to image. Now I'm just giving it to Lorraine to talk about the devices.
Thank you. Okay, so like Dr. Kilich was saying, we're creating these flexible substrates to really go conformal onto the surface of the brain. Okay, and so I just wanted to give some motivation on why we're using the devices that we're using. So why thin film substrates? It's been shown by Kim et al. That as we have more conformal, more thinner substrates, they fit more conformally onto the cortical surface. And this results in a very high signal-to-noise ratio, as validated on ECOG recordings on cat brain, shown on the figure to the right. So now, why are we using organic PDOT on our microelectrodes? So Professor Maliara's group has shown that organic electrodes have been able to detect single unit recordings on the surface of the brain. And the reason behind this is because unlike metal electrodes like platinum, which involve which involve coupling of through a surface capacitor for the charge transfer, PDOT enables the intercalation of ions into the material, which allows both volumetric capacitive coupling as well as Faradaic redox reactions. And so this then introduces a greater charge transfer to the electrodes, which increases the signal of the neural response. Additionally, the signal-to-noise ratio is increased, as we can see, because the impedance is much lower than other metal electrodes. So for the device itself, the way I start fabricating it is I start with a very hard carrier substrate, and I incorporate a very anti-adhesion layer, and then have our base perylene coater layer. I then pattern and deposit our Thai gold, which acts as our metal electrode and leads. And I encapsulate this with another layer of perylene C, add another anti-adhesion layer, as well as a third layer of perylene C, which will act as a sacrificial layer. And I then etch through so that just the contact area is exposed in contact with the brain. The next step is to spin coat the organic conductive polymer PDOT, PSS, and then remove the sacrificial perylene C layer so that only the contact area has the PDOT. And finally, I remove it from the hard surface so we get this conformal thin film multimodal device. So the way we characterize the electrophysiological properties of this device are through electrochemical impedance spectroscopy, which involves flowing a current through a working electrode to a reference electrode and then measuring the potential drop in between over a series of frequencies. And so for our in vitro testing, we use a 3-electrode setup, which we have our silver chloride as our reference electrode. We have a platinum counter electrode, which basically improves the accuracy of our measurements because it reduces the amount of signal that's read in half of the cell. And then our working device is our PDOT device. For in vivo testing, we use Intan technology. And then also, we've also been developing, just improving the stability of our devices through aging studies. And so we kept it in a heated environment at 75 degrees for 2.2 days, which simulated a month long in body temperature. And we were able to show that the impedance of these electrodes did not vary over the month time. And so this is very promising work. And now we'll go over some of the recent results that we've been giving.
No, it's not. Sorry. So we have done some acute experiments with these arrays, and we would like to see like how transparent they are and how we can image. This is a GFP positive mouse on the GAD positive cells, so you can see the cells as green, and also the astrocytes are labeled with SR101, and the vessels are filled with Alexa 680 dextran. So this stack, I actually took it into with two different wavelengths, because this is how they give the fluorescent. And you can see that like with the GFP NSR, we can see somewhat like 500 to 600 micrometer penetration, and with the Alexa 680 we can see down to like 900 micrometer penetration. And you can see on the surface, especially on the right side, the array is giving a little bit of shadow, but since the wires are only 10 micrometer thick, it's just not more than a shadow that any arterial wouldn't give you. And after 100 microns, you can actually start seeing more clearly. Here is another experiment we recorded for electrophysiology, and this is, we have two piezoelectric crystals which are deflecting two different whiskers, and there is a delay introduced in between. And as you can see through the array, there is a distribution of responses. And for this we have I would like to like blow out one of the channels, so I can, this one, show the graphic. Yes. So this is basically we give the first one and then second one only, and then we introduce the delays from 10 milliseconds to 500 milliseconds, and there's a paired suppression before the 100 milliseconds, basically, in this example. So we try to implant these chronically. So this is how we try to do it. So we know that the glass plugs work, and if we can fix the array on the bottom side of the glass plug and attach it to the mouse's head and introduce like a reference screw, we may be able to record from it. This is what we were thinking. And for the other experiments, we were always using like this ribbon cable, because the attachment to the array is easier on the production side. But with the ZIF connector directly, we tried to connect it directly to the head, but it actually required more force than we expected. And the perylene is only 10 micrometer thick, so it just broke up the perylene in the end. And we decided to change the connector. It needs to be something small, it needs to be something light. So we have decided to choose this 36 channel connector from Omnetex, which is going to be plugged into the preamplifier before the Intel board. And this actually allows us to put a reference screw into one of the empty channels as well. So the next step is to try this.